Hey there. Today, let's try to solve this problem called longest alternating subarray after removing at most one element. So in this problem, you are given an integer array nums, and you need to tell what is the longest alternating subarray after removing at most one element. So basically, an alternating subarray is that you start from the first element, the next element is smaller than you, and the next element of that is larger than itself, and the next element of that is smaller than it, and so on and so forth. Or we can start from greater, and then the next one is smaller, and then the next one is greater, and so on and so forth. So there's like two options we can pick, starting from any subarray. And then we can remove at most one element from that subarray, any subarray that we pick. And then, so for example, if we just remove like L plus 2 here, it will just like checking if nums L plus 1 is larger than nums L plus 3. And then this will change to smaller. Because it basically just treat L plus 2 as L plus 3. Just what I mean by removing. So let's take a look at this example. The first one is 2, 1, 3, 2. It should return 4 because the whole entire array is the alternating, because we can choosing like first start using the greater symbol, and then the second one is like smaller, and then the third one is greater. And then example 2 is like this, and then the answer is 4 because, as you can see, like this one is the longest subarray that we can pick. So we are picking like the first one is smaller, this is smaller, and this is greater, and this is smaller, and this should be greater. So we cannot, that's why we cannot extend this one, because otherwise if it is like 5, then we can extend this, and the total answer will be like 5 in length. So yeah, but because of this constraint, the longest we can achieve for this subarray length is just 4. And yeah, and so on and so forth. That's pretty much all for the problem description. Let's think about how can we actually solve it. So okay, in problems like this, we usually want to think about DFS, and then you're given an I. In this case, like, I don't know, the longest alternating subarray starting at I. So with that, we just like the total answer we know is like the max of DFS I, right? And this will be the result that we want because we're considering every starting position. But when you think about it, it's not enough to have just I. For example, we need to know like the next one, if we can, like for example 1, 2, 3. So we need to know if we can do for the next one. So we also need to know is greater. Okay, so if we are using the is greater symbol, then this is valid because we have two options, right? We can do like greater, smaller, greater, smaller, greater, or we can do smaller and then greater and then smaller and greater and smaller, stuff like that. So we just know that we just need to know is greater is true or not. If it is true, then it is expecting the next element to be greater. If it is false, then we're expecting the next element to be strictly smaller. Okay, but is that enough? It's still not enough. We still need to know, like for example, we can remove at most 1, right? We need to kind of pass down this information to the recursion call that if we have used that operation or not, because that would also affect the result. For example, there could be a lot of valid here, but just because this one is kind of blocking the way. And if we kind of remove that, then all this thing, for example, if we want, it will kind of be valid. If that makes sense. So yeah. So we also need to know hashed removed. So once we have that, and then we just, so this is just 0 and 1 is greater, and has removed is also 0 and 1. So as a result, this recursion function, you just look at it, it is still like O(n). So it's more like O than times 2 times 2. But you know, 4 times n is still just O(n). Okay, now let's think about some base case here. Let me remove that. So by the way, this one is just is greater, and then also has removed, and then you just loop through all possibility and then get the final answer. That will be what we are looking for. So let's think about some base case here. Base case. So obviously, if like I equals to like n, or just in general greater than n, we just return 0, because there's no longer alternating subarray starting at this index, because this I index is invalid. And then otherwise you just need to know if it is okay to match I and then I plus 1. So if it is okay to match I and I plus 1, then the current answer is just current answer take the maximum of that to like 1 plus the DFS I plus 1 is greater. We will just string is greater to not is greater, because if we are expecting smaller right now, we will be expecting greater symbol. If we're expecting greater symbol right now, for the next one we will be expecting smaller symbol. And also as we move, will just remain the same. And let's just say this is like okay to match. So what does this okay to match mean? It's very simple. Okay to match I and J. You just want to know, actually we need more. We need is greater as well, because it depends. It kind of depends on is greater value to determine whether or not it is okay to match. So if we are expecting is greater, then we'll just need to know if nums j, which is the next value that we're trying to move from, is strictly greater than nums I, and otherwise it is expecting a smaller comparison. So we need to the next has to be strictly smaller, otherwise we will be invalid. So we have this like helper function, and then also if if it is not okay to match, then it's like has removed. We haven't removed anything yet, and it's okay to match I plus 2, and it is greater. And if that's the case, then we can also consider removing I plus 1 in this case. So 1 plus DFS, and then I plus 2, and then is greater will also be changed, and then as we move will become 1, and so on and so forth, and finally just return result. Yeah, so result initially will be just 1. This means treating nums I as a subarray with only nums I. Okay. Yeah, and then we can apparently do some like DP here or memorization to make this ON. Yeah, that's pretty much all for the intuition for this problem. Let's see how can we actually implement that. Okay, so first we're going to initialize n equals nums sized, and then let me just paste our previous reasoning to here, just so that we are on the same page. Change. Okay. So let's see. So first we need to implement this OK to match helper method. This is just Boolean OK to match. We'll expect I and then J, and then also we need to know is greater or not. I'll just use next greater. So next greater, if it is 1, then it's true. That also means that it is expecting a greater element on J. So if next greater, then just return nums J is greater than nums I, and else we just return nums J is smaller than nums I. So we need to do some boundary check. For example, if like J is greater or equals and then it's not possible. We just return false here, because this is actually possible to reach this condition if you look at here. So because sometimes we're just doing I plus 2, so it could go out of range for the J indexed. So actually we also need to have access to nums as well, so we also need to pass that vector in nums, and then we can start coding. We need to do some DP because we know we have like, let's say we have 3 parameters here, so that's why we have a 3D DPOA. So we need factor, and then this is the 3D array in C++. Just bear with me with the complex syntax here. So the first one is the I, right? The I can go up to n. So I just use n plus 1. Because you know n is like a exclusive. It starts from 0. So if it is n plus 1, the index can go up to n. If it is just n, then the index can only go up to n minus 1. So that's why it's n plus 1. And for the second one, the second one is greater, it's just 2, so 0 and 1. So factor, and so it's just 2. And the last one is has removed, which is also a Boolean value. So it's just 2. And once we have this DP, and then we are going to loop the I, and then we're also going to loop the what's it called? Is greater. And we're also going to remove has remove. So we don't know the order yet. We don't care about that for now. We're just going to copy our recursive call here. Let me just paste the whole thing here. So let me change to C++ syntax. So if I is greater than n, we just return 0. It means do nothing. So you just continue here. So otherwise, result is 1. This one is just treating num_i as a subarray. And then OK to match is just I plus 1. Let me also change that to C++ syntax. And we also need to pass nums as well. And this one DFS, we just change it to DP because it's the same thing. DP is greater as remove. And this one also, let me change to C++ syntax. And then we do like dp n plus 2, and then it's greater. Okay, add some semicolon here and there. And then finally return result, we need to change it to dp I is greater, and also has remove is equals to result. And then finally we need to do this, right? Let me also copy this here. So this is basically do answer equals 1, and then for I equals 0, I less than n, I plus plus, and then answer equals to maximum of answer, and then it's just dp I, and then 0 is 0. So this 0 sample has removed. This is greater. We can also start from is smaller, so it can like be like this. And then finally we just return the answer of that. So let's go back to here. We haven't considered the order yet. Let's take a look how we're going to access the dp value. So it's accessing always dp I plus 1 and I plus 2. So it means that when you are visiting dpi, I plus 1 or I plus 2 should be ready. So how can we make sure that I plus 2 or I plus 1 will always be ready? So the simplest answer for that is we just start from the largest. And I and 0, I minus minus is greater. So we just need to consider this. And then as you can see here, it doesn't really matter. As long as we are doing dpi plus 1 or dpi plus 2, we don't care it's greater order or it has remove order. It doesn't make a difference. So it's greater, it's 2, it's greater, plus plus. It's remove 0, has remove 0, has remove plus plus. Yeah. And that's pretty much it. Let me skim through what have I missed here. And so this n is missing. Start. Yeah, that seems fine to me. Let me just copy this code to LeetCode and submit it. Here. Let me try to run it. Okay, this is missing semicolon. Okay, to match. Okay, it's also missing nums here. Okay, sample test case passed. Let's try to submit. Accepted. And let me just scroll this here. So the time complexity for this one is O(n). Well, because even though you use n times 4, but 4 is a constant again, and the space is O(n) as well. Similar reasoning. I actually don't know why it's so slow comparing to others. Maybe you can let me know in the comment section. But yeah, that's the main idea for solving this problem. Yeah, thanks for watching, and I'll see you next time. Bye.